distinguished panel who represent various aspects of this proposal and can discuss it. There's of course there's of course Robert Raussendorf from who's on the faculty at UBC, and as Patrick already pointed out, he's the person who proposed measurement-based quantum computing on cluster states, and as well as its fault-tolerant incarnation. We have Daniel Litinski from who's at PsiQuantum, and who's worked extensively on quantum error correction in various forms of color codes, Majorana fermion topological quantum error correction. So, and he can comment, I think, about the relationship about this proposal to the work that PsiQuantum is doing. And we also have Amir Safavi-Naeini, who is a professor of applied physics at Caltech. He works on photonic and microwave devices for quantum sensing and and computation. And so again, welcome everybody. And perhaps we can start with a few minute, your few minute. Give everybody a few minutes for your reaction to the talk, as well as any of these topics. So maybe we can start with Robert.
Actually, can I throw in one minor correction?
Yeah.
Which is just that Amir, I'm lucky to have him as my colleague at Stanford rather than at Caltech.
Oh, sorry. Yeah.
But he does work on the Caltech campus quite frequently because he also has an affiliation with Amazon.
Yeah, I'm sorry. I meant to say Stanford, but I probably misspoke. So sorry, Amir. And thanks for the correction, Patrick. Would you like to say a few words, Robert?
Yeah. Oh, thank you. Good. So I think the critical part of the architecture, the Achilles heel, if you like, has already gotten considerable attention, both by what Andrew said and Umesh, what you asked about, namely this fact that the length of the DLA line scales with a square of the size of the cluster state. So this is what's preventing you from a threshold result. And well, I suppose I think it's a good solution. What was already mentioned, that why not have various emitters working in concert with one another? I mean, that might kind of ramp up technological difficulties. I mean, now these emitters need to be scheduled to work perfectly in sync. So photons from one emitter have to go into the delay line of the other emitter, and so on and so forth, and that has to work at the appropriate times. I can imagine that this is more difficult, but maybe for people like us, we delegate those difficulties to others. Yeah. So So I think that is, if you want to go towards fault-tolerant quantum computation beyond keeping a qubit alive for a very long time, I think that would actually be helpful. So good. So yeah, for me, that was the central question, but it has already been pretty much addressed, modulo maybe some technical difficulties. So maybe a tiny technical thing that, oh, well, maybe not, a technical thing that I would like to get back to is, I was very surprised what you said about the error model. I mean, you said, okay, so now here we're doing everything different from what you would normally do. You have one qubit interact with many, which could propagate errors badly. But then you said, okay, what we are only interested in, and that's of course correct, is error modulo cluster state stabilizer. We are interested in equivalence classes of errors, and if the equivalence class has a local error, then that's good. So if we have the time I'm surprised that this holds. And if we have the time, perhaps we could go back to the slide when you showed this. Namely, you showed an X error happening directly after Hadamard. Yeah, that's the first error you showed. And what one could compare this with is an X error happening one time step later, namely after the conditional phase gate that happened. So if you would propagate the former error one step forward in time, compared to the second error, it would give you an additional sigma z. Yeah. So and that will not further propagate because z's do not propagate through conditional phase gates, which I believe are that. So it's really surprising to me. I want to emphasize this, that the technique actually works, and you can map everything effectively at the end to a local error model. So I'm really surprised by that finding, and I wonder whether that would persist if you have multiple emitters working in concert. Good. And another thing, I would like to maybe hear more, but there's other people here on the panel who can ask more probing questions about it, is the interaction. When a photon comes back to interacting with the emitter again. So, I mean, you want this to result in a very specific interaction and also a very strong interaction. Yeah, I mean, it has to be conditional phase gate, and how you would model, I mean, how realistic is this in physical devices? Okay, so I think that is my questions for this panel discussions, and hopefully we can get back to them in turn.
Great.
Some of them.
Thanks, Robert. Well, possibly if you move on to Daniel, possibly, for your comments, as well as addressing the question that came up earlier about how all this relates to the work at PsiQuantum, and possibly also Robert's question, maybe. So you have a lot on your plate.
Yeah. So first of all, thanks, Patrick, for the nice talk. That was I enjoyed it very much. And I think what I really like about this kind of architecture is that it really highlights both the advantages of photons and also the advantages of what you can get from combining different types of hardware approaches. So photonic with non-photonic components. And on the photonic side, I think your architecture really nicely demonstrates how the use of these long, low loss photonic delays, specifically optical fiber, how this can really significantly reduce the number of components that you need to build this kind of large scale quantum computer. And well, perhaps sort of this already relates to something that Andrew asked, in this interleaving approach that we talk about at PsiQuantum. This is sort of one of the central advantages that we would like to exploit from photons, that you have this kind of memory capability in some sense with photons. Maybe one thing that I wanted to add to what others said about this regime of using multiple emitters. So I understand that you focused on how to build a qubit and how to sort of store one qubit. But in principle, there's sort of no conceptual difference to building a cluster state for one qubit or building a cluster state for an entire computation, because they're both cluster states. You're just sort of performing different types of measurements. And there was in some sense this, well, people highlighted that if you want to have a constant number of components, or if you're just using one single emitter, you don't want this to sort of be a limiting factor when you have to go to large code distances. But in the context of a full, entire quantum computation, I would say that there's also a secondary consideration to keep in mind. And essentially, the kind of consideration that I would like to highlight is that known useful quantum computations are very large, typically, starting at hundreds or even thousands of logical qubits. And they also have extremely many operations, like 10 to the 10 non-Clifford gates, whether it's T gates or Toffoli gates. But if you really think of this in terms of a cluster state, the kind of cluster state to have in mind is is a huge three-dimensional cluster state, something consisting of many two-dimensional layers, trillions of layers, but with millions of qubits, or let's say 1,000,000 qubits in each layer. And if you wanted to generate this using a single quantum emitter, then, well, first of all, you would need a delay that can contain 1,000,000 qubits or 1,000,000 photons. So how to build this is one thing, but even if you did, you would have to ask yourself what this implies for the speed of the quantum computer, because you need to reach a certain number of logical qubits to have a useful quantum computer, but it also needs to be fast enough to do anything useful. And so these long delays, they're really great at getting lots of qubits out of every component that you have, but they also slow down the quantum computation. So in some sense, it's sort of a linear space-time trade-off. And if this one quantum emitter, if it can process one qubit every couple of nanoseconds, and you need to process 1,000,000 qubits to generate a layer of this cluster state, then it corresponds to this kind of slow millisecond code cycle, and this could be a relatively long time in terms of quantum computation. So one thing I would be sort of curious to hear about also. Hear more about what the motivation was behind having really a constant number of components, and really what the notion of constant means. Well, we discussed this, I suppose. Yeah. So I could perhaps also comment later on this. Well, someone asked about fusion, how this relates to this fusion-based quantum computation approach. But yeah, we could also postpone that to later.
Let's see. I guess Patrick, do you want to? You responded to some extent already, right? In terms of saying you were thinking not one emitter but multiple emitters, but maybe was there more specific? Sorry, we can't hear you, Patrick. You're muted.
Yeah, so I could certainly respond partially. Robert had a number of questions, and Daniel also. Amir hasn't had a chance to speak, so maybe I'll just respond quickly to Daniel. And yeah, I completely agree. About the observation that by forcing every interaction to go through this one emitter, you linearize the entire computation and the preparation of the entire quantum error correcting code, and you pay a price in terms of the speed of the computation. So the motivation for us, I think, was mostly kind of the idea was a demonstration of an extreme case, right? Like that we really wanted to ask the question, how far could you go? And if your goal was just to make the fault-tolerant qubit, how simple could the architecture be? With the longer term vision being once you know that extreme point, and and I think, well, at PsiQuantum you've probably been optimizing this pretty hard, but for a lot of the people in the quantum computation community, they sort of think about the model where you have a bunch of individually controllable qubits, and every one of them has to be kind of controlled and interacted with essentially at every time step or nearly so, versus this opposite extreme where you actually just interact one at a time with the data qubits, and the data qubits have no ability to interact at all. Once you've done that, then you can try to interpolate, right? Like given your technological capability, you can say, well, with what we have available, we're going to optimize our ability to build a useful quantum computer, and one that is actually fast enough to be to give us answers on a time scale that is interesting by locating ourselves here. And I think that opening up that realm of possibility for performing that optimization was basically the motivation.
Amir, would you please? Yeah.
Thanks. Yeah, thanks. Actually, my first comment was very much related to what you just said now, that I think this is like if you can sort of draw a map where on the x-axis you have sort of a control complexity, and you can control every single one of your qubits, and that has a control complexity of n, and then this has a control complexity of 1, and then there's that space in between that I think is really worth exploring. And I also want to say that I really enjoyed your talk, and I think it's also very timely, I think, because there's, I think on the hardware side, there's starting to be a lot more interest in developing kind of memory elements. There's serious efforts to build quantum networks now, and that's memories will be an important part of that. So hopefully we will see a lot of advances on the hardware side on developing memories that are compatible with superconducting qubits that can have this coherence time that gives you this type of advantage. And then I also, one comment is just from experiments with one type of memory element, which is the mechanical oscillator, which I'm more familiar with. It does seem like the type of errors that you get in those systems, you're much more likely to get dephasing errors. So the kind of record coherence times for nanomechanical resonators made out of silicon are currently held by the Caltech group, Oscar Painter's group. And they see T1 times around a couple seconds, but their T2s are around 1 millisecond. And that's sort of expected from the sources of decoherence that you would have in these devices. It's typically two-level systems, same story that you have in superconducting qubits. So you have a lot of defects in the structure that behave like two-level systems. And if your device is small enough, the density of these defects is such that your resonance just won't hit any of them. But they still fluctuate, and those fluctuations cause fluctuations in the frequencies of these oscillators. So you can get reduction in the T2 time because of that, but the T1 is not affected. One question is, can the encoding, or I guess in this case, can the encoding be done in a way that kind of takes this bias into account at some level? And then another question I had, I think maybe is related to Andrew's main point, or one of his points on what you call a component, which is, so in this case, you have, you're calling the whole delay line a component, and that component is scaling, and now you have more and more modes in that component, which is fine, because I'm okay with that, because, sure, there's some challenges as you make that larger and larger, but in the end, there's just one point that you have to really control with wires going down. So it's, it does scale differently than a superconducting system, where as you scale it, like, you have just way more cables and way more processing and everything that has to be done in parallel. So, but my question was, in the how does the error model, what is the error model in that component? Because I can imagine, for example, depending on the type of delay line. So let's say if you have a superconducting delay line, if I have a cosmic ray that comes down and hits some part of it, and then generates a bunch of quasi-particles, that would affect the temporal modes nearby in some correlated way. You might get bit flips on qubits 10, 11, 12, 13, but nothing around there. And so there's some, I wonder if your error model takes that into account, or how much sort of effect you would expect there. And I guess that's really related to developing error models for those components. Yeah, those are my questions. Thanks.
Thanks, Amir. That was very interesting. Actually, may I jump in with a naive question from the viewpoint of a theorist? So, what can somebody address this question of how should I think of a delay line? So should I just be thinking of, well, it was clear, Amir, from your conception of it, that it's, my naive view, well, it's a fiber, a very long fiber with photons going through. Well, this is too naive. So how do we think of what a delay line is, and what are the prospects of building, are there natural bounds on, you can get delay lines this good, and going beyond that would be very hard, or well, there's no end in sight, etc. As well as well, the other question I had is something that you asked, but it would be good to touch on it, which is what are good error models for delay lines, now that there are a large number of qubits going, being shuttled through them simultaneously. So how would one think about all these questions?
Yeah, I guess for the delay lines, so there's, probably the best delay line in the world is the optical fiber. So it's a piece of glass that's kilometers long, and in an optical fiber you have losses that are 0.15 dB per kilometer. So you make it, if you want to get to 20%, you would probably have to make it, I don't know, like 5 kilometers long or something. And then the disadvantage of the optical fiber is that the speed of light is very high, and so your temporal modes end up being fairly large. So when you go to acoustic waves, you can make something that looks a lot like, imagine just a long string on a chip. And vibrations on that string, you generate them on one end of the chip, and they propagate to the other end, and they come back. And the speed of sound on a chip is something like 5,000 meters per second, which is 5 orders of magnitude slower than the speed of light. So the length of these delay lines ends up being much smaller. The losses, according to the Caltech results, are something like 1 dB per kilometer instead of 0.15 dB per kilometer. So, but this is comparing something that a graduate student made to something the industry is optimized for 40 years and Nobel Prizes have been awarded for. So it's sort of, I think there's some room to improve there. Yeah, and then the way that the excitation gets coupled to, let's say, a superconducting qubit, you have to, superconducting qubit, depending on the type of qubit, with transmon qubit, there's an electric field that oscillates at, let's say, 5 gigahertz, and you want that electric field to generate a force, to generate the motion on the chip, and you can, for that, you can use like a piezoelectric material which converts electrical fields into force. And that's something that has also been developed in the last few years.
Great.
So I'll just throw in one little comment. I didn't show the slide, but we also worked at we analyzed the errors in the delay line under the assumption not just of loss. We also did the case where the errors were dominated by dephasing in the delay line. And what we found was that we were within a factor of 10, I think, of the kinds of dephasing rates that Amir was seeing in his latest experiments. And just to reiterate, these types of systems where you had where people are looking at these delay lines and acoustic or for acoustic phonons, I think that has been optimized for maybe 5 or 10 years. Just as you said, by a small number of people working in universities. And so you're looking at, on the order of 5-10 papers, as opposed to thousands of people devoting their lives to it in the case of optical fiber. So you're seeing significant percentage improvements, year over year. Mm-hmm. There was a significant backlog of questions. So maybe I'll go back, maybe treat it as a stack. So Amir had asked about encoding for bias. So the codes that we're using right now treat dephasing, are not optimized for dephasing errors. They're as good for handling errors in one basis as another, but you certainly can design codes that are better at correcting for one error basis at the expense of another one. In the case where errors are dominated by dephasing, that's worthwhile. And I think actually that Isaac, working with an undergraduate student, has been looking at that, and there's some preliminary results that look like something like the Bacon-Shor code may actually work well in that regard. And so I can't say anything for sure, but that's a direction that there's definitely unexplored space. And for correlated errors, yeah, so the error model that we've been looking at is just independent errors at every time step. And so we haven't looked at correlated errors. If you had a situation where a cosmic ray, as you said, a cosmic ray resulted in a spray of quasi-particles and a significant fraction, it corrupted a significant fraction of the qubits inside a delay line, it doesn't seem like a huge stretch to imagine that you might actually get a logical error in that case, right? That you could get something that looks like a topologically non-trivial chain of errors, but we'd have to look at that. So Robert had a number of questions and comments, and so I'll try to go through those. So he was asking about the threshold result, and I would like to push back a little bit on the need for a threshold result. Just that I think this goes back to Andrew Steen. Maybe 20 years ago, he wrote this paper in which he actually asked not about thresholds, but just about using specific error correcting codes and asking what logical error rates could be achieved with those specific error correcting codes without worrying about thresholds. That for any given computation, there's a necessary error rate, and as long as you get below that error rate, then you're fine. And so we were looking at error rates of 10 to the minus, again, 10 to the minus 15 with cluster states. I forget exactly how big they were, but they were maybe on the order of 20 by 20. And so that's a logical error rate where you're unlikely to require anything better than that, I think. And so I wouldn't worry so much about the threshold, the fact that this is not a strict threshold result. So Robert wanted to go back to the slide asking about the X error after a conditional phase gate. So I can do that quickly. I think I actually even have slides for that. So this one here.
Many slides on that. Mm-hmm.
Okay, so he asked about, I think, I want to make sure that I can see you here. So you're asking about what would happen if there were an X error after some of the conditional Z gates.
Yes,
and
correct.
So this is actually an example of that right here. So I'm imagining there's an X error after these two, there's a Hadamard and then two conditional Z gates, and then an X error. So an X error on the emitter right here. And because of the stabilizer structure, there's a stabilizer which is X on the emitter and Z on 4, Z on 7. That propagates to a Z on 4, Z on 7. And then the subsequent Hadamard and controlled knot will swap the emitter into position 10 at this point. Oops, okay, I don't have a slide for the swap. But this emitter is going to get swapped into position 10. And so 4 and 7 are going to be neighbors of 10. And that's what ends up happening, that there's going to be a collection of physical errors in the cluster state that are in the neighborhood of a single qubit in the cluster state. And in this case, there'll be in a neighborhood of qubit number 10. Does that answer that question?
Yes, I mean, I guess I would have to
yeah, this is just an example. I mean, the actual paper, gives the proof in all generality, but this is the idea.
Good, thank you.
Okay, and go back to Robert's list.
There was one, maybe perhaps one question we were going to come back to, which is how what you propose relates to what PsiQuantum is doing.
I'd like to hear about that too, actually.
Yeah, then maybe let me comment about sort of how this is similar and different to fusion-based quantum computing. I mean, I already pointed out the similarity that where fiber plays a prominent role, but fusion-based quantum computing is sort of this, it's a different model of computation that we have in mind at PsiQuantum, because it's the model of computation that most naturally, in some sense, most naturally describes the components and operations of the hardware that we have in mind. So this goes along the lines of what Patrick mentioned in the talk. Everyone is familiar with the circuit-based model of quantum computing, where the objects are static qubits and entanglement is generated through 2-qubit gates. And this is something that really naturally describes reasonably naturally describes what you would do on something like superconducting qubits. And in the talk, we've seen another model of computation, which is this measurement-based quantum computing with cluster states, where really the entanglement is in the objects, these large entangled cluster states. They're responsible for entanglement, but the operations, they're just disentangling single qubit measurements. So fusion-based quantum computing is a model that's somewhere in between, where sort of both the objects and operations are responsible for entanglement. So in fusion-based quantum computation, a quantum computation corresponds to some arrangement of few qubit resource states. So constant size, think of like something like a 20 qubit resource state, and fusion instructions between pairs of qubits from different resource states, fusion being a 2-qubit measurement. So why do we have this kind of, why is it somehow important to define a model like that? Because the kind of components that we have in mind for a photonic quantum computer are essentially two types of components. One type is and in some sense, they're sort of similar to what we've seen today. One type of component is a resource state generator, which is an emitter of not of single qubits, but of these few qubit resource states, something that on a clock cycle, say every nanosecond, produces a few photon entangled state. Not a very small number, but a constant size number, like something like 20 photons entangled in some specific way are produced by a resource state generator. That being one type of component, and the other type of component being, in the talk we had a detector, which is sort of a single qubit measurement device, but in fusion-based quantum computing, it's a 2-qubit measurement device that essentially performs type 2 fusions, which are essentially 2-qubit Bell basis measurements. Okay, so sort of both of these components are responsible for entanglement in some sense. Now there's no, fusion-based quantum computing is no more powerful than sort of cluster state-based quantum computing or circuit-based quantum computing. You can translate from one to the other. It's just about what sort of naturally describes the kind of, the kind of components that you want to use to execute your quantum computation. And so, I guess we're in this interleaving, in this paper about interleaving, there's an architecture is described that's sort of, tries to exploit fiber delays or low loss optical delays in the same kind of way, where you can use optical fiber as some sort of temporary memory to drastically reduce the number of resource state generators that you need to build such a large-scale quantum computer. So essentially, you can think of a large-scale quantum computer in this fusion-based quantum computing setting as a network of many of these resource state generators. They're sort of similar to these emitters, but they produce something more complicated than just single qubits. And by using optical fiber as a temporary memory, you can reduce the number of, of these resource state generators that you need to build something that's equivalent to a 1,000,000 qubit device. So for instance, instead of, maybe to also comment sort of what does a optical fiber delay line look like? Well, 1 kilometer of optical fiber, speed of light in fiber is 2/3 of the speed of light in vacuum, but it's, you know, if you send in photons fast enough, if you send in photons every nanosecond into an optical fiber, then you can really think of a 1 kilometer long optical fiber delay line as sort of this piece of optical fiber as something that stores 5,000 photons at any given time. You know, there are 5,000 photons in this piece of optical fiber, 1 photon entering every nanosecond. And essentially, you know, if you sort of design your architecture the right way, similarly to what we've seen today, then you can use this to get this factor of 5,000 reduction in the number of components that you need to build. Yeah, maybe it's sort of an additional comment. I think if you wanted to make Andrew happy and really provide sort of a threshold result, you could still do this in this sort of multi-emitter regime. If you were, you know, if you just uncoupled the code distance from the length of the fiber, from the length of the delay line that you want to use, because essentially, you know, the task is to produce some large cluster state, and to use a maximum delay length that still allows you to do that below some sort of error rate. And you know, how you partition this large cluster state into smaller chunks doesn't need to depend on the code distance, because these are sort of two completely separate numbers. So there is still a threshold result in there. It's just not sort of the way it's, I suppose it's not something that you can present with just a single component then.
Great. Patrick, do you have anything further to say about that?
Yeah, well, I definitely agree. As I said, we haven't thought carefully about how to stitch together these little pieces of cluster state into a larger cluster state, but it clearly is possible. And the question is just how you would do it in the most intelligent way. And once you do that, it does start to seem quite similar to your architecture at PsiQuantum, but perhaps not optimized for the kinds of measurements that you can perform on the photons. Like it sounds like the 2 photon measurements in the Bell basis is a useful primitive for actually creating entanglement that we're not trying to exploit here. But that if you thought of this in terms of multiple emitters, each emitter capable of making a chunk, each emitter would be very much like one of your resource state generators. And then there's this extra fusion process, which is supposed to stitch them together into some larger resource state, which we actually haven't even pursued. From an experimental standpoint, I expect that there would be there was a question about the quality of the controlled Z gate when a photon or phonon comes back to the emitter. And if the phonon or photon is coming back to the same emitter that generated it, then I would expect the interaction to be better than it would be coming to a different emitter, just because the profile of the pulse is going to be exactly matching the pulse, because it was generated by the same emitter that it is now interacting with. It's going to be optimized, and so there could be additional difficulties that aren't present at the abstract level when you try to stitch things together, but might be present at the kind of physical level in terms of engineering the quality of the gates. And we'd have to check, as Robert said, whether the error model in this picture would remain local if you actually started trying to stitch together multiple emitters. I suspect that it would, but we'd actually, one always has to check.
If I could just inject for 3 seconds, exactly local would not be necessary because you're dealing with a topological code. I mean, you can live with 3 local errors, for example.
Live with what? Sorry, what kind of local
errors? Yeah.
Yeah.
3 qubit Paulis, they wouldn't really bite you.
Oh yeah, right. Like our errors do appear in little clusters, or clusters is a bad word, but in neighborhoods of a single qubit rather than being just isolated individual errors.
Oh, okay. But
yeah.
Thank you.
Great. So if there are any final comments, because we are pretty close to the end of time for the panel. So,
given more time, I would have liked to discuss these catastrophic events, and the fact that you have a 5-kilometer delay line, actually maybe that helps you. If so you can, I mean, normally that would be coiled up, I suppose, this photonic line, but I mean, you could actually lay it out in space, at least around your lab, and maybe that helps actually with these catastrophic errors. But I don't want to start another discussion at this moment. To be continued.
Anything else to add? Okay. Well, if not, then thank you, Amir, Daniel, and Robert, for a very interesting panel, and thanks a lot, Patrick. It was a beautiful talk again, and really enjoyed it.
Well, thank you for organizing this. I really enjoy this format. It was a lot of fun.
Great. So see you all next week. Next week we have Misha Lukin, who will speak about exploring new scientific frontiers with programmable quantum simulators. I guess that's his 200 qubit two-dimensional arrays, I guess. But so see you all next time, and thank you very much.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye.
Thanks, everyone. Bye.